Hi there and welcome. I'm really glad you're here. This is Introduction to OBD2 and Electronic Vehicle Diagnostics, a course that has been running strong for almost 20 years. Back when we started, this course was designed specifically for experienced mechanics. People who knew engines inside and out, but were starting to come to grips with all new electronics and onboard diagnostics showing up in modern vehicles. And wow, things have changed since then. Over the years, this course has been taken by hundreds of learners, from seasoned professionals to DIY enthusiasts. Over the years, this course has been taken by hundreds of learners, from seasoned professionals to DIY enthusiasts. It's evolved with technology covering everything from the basics of OBD2 to real-world diagnostic strategies that you can use in your home or workshop. And now, for the first time, the entire course is available here on YouTube completely free. That means that anyone, anywhere can get access to this knowledge on demand. So whether you're just starting out or you're a veteran wanting to brush up on your skills, you're in the right place. Don't forget to hit subscribe and give the video a thumbs up if they help you out, or drop a comment or question. I'm always keen to hear from fellow learners and techs.
Introduction to OBD2 and Electronic Vehicle Diagnostics. We will cover the following scope points during this course. Electronic Vehicle Diagnostics. Under this, we'll cover automotive buses, electronic communication basics, and electronic control units. Under diagnostic scanners, we will cover DTCs, live data, actuations, adaptations, service resets, coding and programming, key coding, and chip tuning. Under OBD2, we will look at the history of OBD2, DTCs, DTC formats, communication protocols, OBD2 modes, freeze frame data, pending DTCs, monitors, and readiness tests. For the advanced part of the course, we will recap on how engines work, we will look at how faults are detected, we will look at the monitoring of signals, we will define circuit faults, and we will look at drivetrain layout. We will also look at system diagnostics, fault codes in general, and then finish off with a general summary. Electronic Vehicle Diagnostics. We will start by looking at electronic communication within a vehicle. We'll then look at communication between the vehicle and a scanner, and then we'll look at the diagnostic scanners themselves.
Electronic control units, ECUs, are used in modern vehicles to control and monitor vehicle operations. Different names are used to describe ECUs depending on the manufacturer. Below are examples of different terms used to describe the engine controller: ECM, PCM, etc. Do not get too caught up on the specific terms used, as they vary from manufacturer to manufacturer. Rather, pay attention to each vehicle and system as you perform the diagnosis. This is a typical ECU schematic. This shows an engine controller, however it can be any ECU. ABS, transmission, or suspension will have the same layout. All ECUs will have input from some sensors. The input from the sensor will be analyzed by the control unit, and it will use the data to decide on the output, which will be used to control the actuator. In the case of the engine controller, the input may be, for example, from a MAF sensor, which will be an indication of engine load, and this will be used by the engine controller to control the actuators, which may be the fuel injectors or ignition timing. Automotive buses and vehicle communication. Automotive buses describe the method used to transmit electronic control signals between controllers in a vehicle. An automotive bus is defined as a multiplex wiring system, which reduces wiring by transmitting and receiving multiple signals over the same signal bus. The multipurpose bus replaces individual wires performing the same function. Automotive buses are basically defined by their speed, Class A being 10 kilobits per second, Class B 10 to 125 kilobits per second, and Class C 125 to 1 megabits per second. Class D systems may be faster. Examples of automotive buses: emissions and diagnostics. These buses handle emissions and diagnostics information. Mobile media. These buses handle mobile media equipment information. X-by-wire. X-by-wire is the collective term for the addition of electronic systems into the vehicle to enhance and replace tasks that were previously accomplished via mechanical and hydraulic systems. For example, drive-by-wire. The SAE J1815 bus is a Class B protocol developed in 1984. It has two forms: a two-wire 41.6 kilobit per second pulse width modulated differential approach, and a single-wire 10.4 kilobit per second variable pulse width approach. This will be discussed in more detail under OBD2. Media-orientated systems transport is a multimedia fiber optic point-to-point network. The MOST bus provides an optical solution for automotive media and entertainment networks, for example video and CD. Local Interconnect Network, LIN, is used as an in-vehicle communication and networking serial bus between intelligence sensors and actuators. LIN bus is a Class A protocol. CAN, Controller Area Network. CAN is implemented on most new vehicles. A vehicle may have one or more CAN bus implementations. A low-speed Class B CAN bus may operate window and seat controls, while a high-speed Class C CAN bus may be employed for engine management or brake control. CAN bus will be discussed in more detail later in the course. The OBD2 bus defines communications protocols and a standard connector to acquire data from passenger cars. OBD2 data is defined by the SAE J1979 standard. Communication between the car and the scanner. The Universal Asynchronous Receiver Transmitter. The UART controller is the key component of the serial communication subsystem. The UART takes bytes of data and transmits the individual bits in a sequential fashion. At the destination, a second UART reassembles the bits into complete bytes. This is basically an analog to digital converter. The working of an analog to digital converter is beyond the scope of this course. However, the diagram gives a brief description. You may want to research further online. Asynchronous transmission allows data to be transmitted without the sender having to send a clock signal to the receiver. Instead, the sender, the diagnostic tool, and the receiver, vehicle ECU, must agree on timing parameters in advance. In practice, special bits are added to each word which are used to synchronize the sending and receiving units. Because asynchronous data is self-synchronizing, if there's no data to transmit, the transmission line can be idle. So, under normal conditions, the data pins on the diagnostic link connector do not transfer any information. The ECU must first be initialized in order to start communication.
Welcome back to part 2 of our training series, Introduction to OBD2 and Electronic Vehicle Diagnostics. If you've made it this far, you already know how critical vehicle electronics and communication networks are. Now it's time to put that knowledge into action. We'll take a closer look at the core functions that almost all diagnostic scanners share, including reading and clearing diagnostic trouble codes and viewing live data streams.
Introduction to OBD2 and Electronic Vehicle Diagnostics.
When a malfunction occurs, a diagnostic trouble code, DTC, will be set on the ECU to record the problem. These DTCs can be read using a diagnostic scan tool. A diagnostic scan tool is a computer used to communicate with modern vehicle electronic control units. There are a few different types of diagnostic scanners: the PC-based interface, the handheld all-in-one scanner, and the basic OBD2 code reader. The pros and cons of different scanner types. In terms of durability, The handheld is most rugged, designed with covers and protection. The PC-based, the interface is usually rugged, but the laptop PCs are quite fragile. The code reader can be rugged, but some are fairly delicate. In terms of mobility, the handheld is usually very mobile. PC-based, more cumbersome due to laptop and cables that must be carried around with it. The code reader, usually very small and mobile. In terms of software, the handheld, it has a fixed operating system and is usually very reliable. Update by connecting to a PC or by removable media. It has limited data storage. The PC-based stuff, specific software for the interface may have specific operating system and PC hardware requirements. For example, Mercedes-Benz Century can only be run on an IBM T30 computer. A positive, though, is unlimited data storage. The code reader is usually fixed and limited to very specific functions. In general, the handheld is the best universal tool, but is also the most expensive. It has limited screen resolution, but requires limited computer knowledge to operate. The PC-based stuff is usually the best for individual makes, but often have setup issues. They require a good PC knowledge. They have unlimited screen resolution and software application options. The code reader is a cheap solution for quick diagnostics. It has limited functions and is easiest to use. Diagnostics terminology. The diagnostic link connector. It refers to the port or the plug used to connect the diagnostic scanner to the vehicle. It varies on older vehicles, usually found in the engine compartment. In newer vehicles, it is standardized to the OBD2 16-pin found within reach of the driver. DTCs, diagnostic trouble codes, records the indicated faults on a specific electrical circuit. Several names are used interchangeably by different manufacturers to indicate fault codes. Fault codes, fault memory, trouble codes, troubleshooting, and self-diagnostics. Listed are the main functions of a diagnostic scanner. They will be discussed in more detail over the next few slides. To read diagnostic trouble codes. This is the main and most basic diagnostic function. The scanner will retrieve the DTCs stored in a specific control unit. The definition of the code is interpreted by the software. The scanner must also be able to clear or reset DTCs. It must be remembered that fault codes are the results of tests that the ECU runs on specific circuits. In other words, the system must be designed to perform a specific test. Sensor and actuator failures are easiest to detect as the ECU is constantly communicating with them. Unless there is a specific test, wear-type failures are not picked up as trouble codes. So there's no fault code for when a car is losing power or has a flat spot or is losing compression. If a car has a specific wear sensor, like BMW brake pads, then only will you see a fault code. This is an example of a diagnostic trouble code printout. The fault code is 18038. The definition of the fault code is accelerator position sensor, signal too low. There is further information given by signal too low. The G79 figure is a position indicator which will show the position of the sensor on the wiring diagrams or in the workshop manual. Live data. Data parameters to track the sensor and actuator data from the control units. These values indicate the actual measurements at the sensors and can give indications of temperature, flow rate, pressure, etc. After fault codes, live data is the next most useful way of diagnosing a problem. With experience, one can identify what certain values certain sensors should be reading, and use this data to identify malfunctioning sensors. Note that different terms may be used by different manufacturers to indicate the same thing. Data stream, actual values, data monitors. This is an example of live data. It shows the voltage at terminal 30 is 13.6 volts. The voltage status is 10. Terminal 15 is on, and the S contact is activated. Actuations are verification tests to confirm the functionality of a particular electrical circuit, sensor, or actuator. This is done by switching on or off circuits using the diagnostic scanner. Once again, several names are used interchangeably to indicate actuations by different car makers. Actuations, functional tests, active tests, final control diagnosis, output tests, and drive links. So in the old days, if a customer told you their car was overheating and you wanted to test the fan, you would have to run wires from the battery to the fan. Using the actuation function, you would simply select fan relay and switch it from the diagnostic scanner. The fuel pump could also be tested in this way. The systems that can be tested vary from vehicle to vehicle. Adaptations. To calibrate the performance parameters of certain control units or components to factory defaults. To adjust parameters such as idle RPM, suspension level, etc. Names are used interchangeably for the same thing by different manufacturers. Control unit adaptations, basic settings, work support, and calibration. The most common example is the throttle body on drive-by-wire VW vehicles. If the throttle body is removed during servicing, the throttle flap may move during the process. When it is replaced, the system may think that the flap is at 0 degrees, when it may actually have moved to 5 degrees. This may result in idling or fueling issues. Throttle body adaptation would recalibrate the system and ensure that the throttle flap is set at 0 and matched to the system. To reset the service indicator for the vehicle, such as oil service or service reminder light. Note that a service reset is a different operation from a fault reset. On most vehicles, a service reset can be done without a diagnostic scanner if the vehicle is within its service schedule or slightly over, by a procedure on the dashboard. A service warning is an information display based on time or distance read from the vehicle dashboard. Thus, the service reset is an instrument cluster function and not an engine function. Component coding. This refers to changing the parameters of a control unit to match a specific vehicle. This usually needs to be done when exchanging or replacing components, for example, an automatic transmission. The purpose of coding is to program a control unit so that it knows in what vehicle it's in and with what other controllers it should be communicating with. When a control unit is fitted in a vehicle, it must communicate with other control units. For example, speed data is transferred between the ABS control unit and the transmission. The coding of the control unit tells each control unit with what other control units it should be communicating and what information should be receiving and transmitting. If a unit is not coded correctly, it will report fault codes if it is looking for information from a control unit that is not available. The coding value 13121 gives the control unit the information it needs to function. It defines the control units that the control unit must communicate with. The coding process varies from make to make. It is good practice to record the coding of a control unit before removing it. Thus, it can be easily written to the new control unit once installed. Key coding. Most modern vehicles make use of a transponder key that is linked to the vehicle's ECU. When new keys are cut or an ECU is exchanged, it's necessary to match the key to the ECU. Key coding is a specialist programming function that is available on most professional diagnostic machines. Certain vehicles will require a PIN code to perform the key coding function, which the diagnostic scanner may not be able to give you. The PIN code is usually obtained from the vehicle manufacturer. Programming refers to the correcting or recalibrating of the ECU data due to software changes by software update. Programming is also called flashing. Modifying of the ECU data for more performance or chip tuning is also a form of programming. Chip tuning refers to the process of modifying a vehicle's programming in order to achieve performance or economy gains. It is usually done in conjunction with other mods, like exhaust or intake mods. In the past, chip tuning was performed by physically changing a chip in the ECU of the target vehicle. In the modern vehicle, the chip tuning refers to the three following steps: downloading the information from the vehicle's ECU, modifying the ECU file, then loading the modified ECU file back into the vehicle to achieve the desired performance enhancements. A flashing interface or device must be used to perform the file transfer between the ECU and the storage device. In most cases, the flashing device is not a diagnostic scanner and will not perform diagnostic functions. Examples of flashing devices are the KWP, SPI, and BDM units. This is an example of the hexadecimal code within a control unit that represents the data within it. This is the same hex code with some line numbers added and some converted to ASCII. You can see some data that looks like a VIN number. Here you can see some patterns. These patterns form the ECU maps that determine how the systems perform. Drawn as a 3D graph, this is how it looks. By modifying the shape of the graph, one can change the performance of the systems. Sensor simulation. Sensor simulation is an advanced function available on certain diagnostic machines. It refers to the capability of artificially simulating the functioning of a specific sensor. For example, if a vehicle is showing a fault code, the simulation function will allow you to artificially input the correct sensor output to the ECU. The sensor simulator can allow you to confirm whether a fault code is caused by a sensor failure or a wiring fault. The advantage of this is that if a sensor is not faulty, it saves on unnecessary replacements.
Controller Area Network Diagnostics. CAN electrical systems began to appear in newer vehicles in around 2003. It is a communication standard that allows the various modules and computers in a vehicle to talk to one another via a common data bus circuit in the wiring system. CAN was created in 1984 by the Robert Bosch Corporation. The first production application was in 1992 on several Mercedes-Benz models. Today it is found on most new vehicles. In a CAN bus system, all the control units are connected to each other by a common set of lines. Due to the linear structure of the network, the CAN bus is available to all other modules in the case of a failed or disconnected control unit. This is referred to as a tree structure, with each module occupying a branch. The main bus is referred to as the trunk, with the individual control units occupying the branches. Every module that's attached to the data bus network is capable of sending and receiving signals. Each module or node has its own unique address on the network. This allows the module to receive the inputs and data it needs to function, while ignoring information intended for other modules that share the network. When a module transmits information over the network, the information is coded so all the modules recognize where it came from. Data is sent as a series of digital bits consisting of zeros and ones. If you looked at the data on an oscilloscope, you would see a square wave pattern that changes between a high and low voltage reading. The diagram shows CAN bus signals as they would be seen on an oscilloscope. Two channels are shown, CAN low on one channel and CAN high on the other. The CAN low is normally at a higher voltage, 2.5 volts shown, and goes low, 1.5 volts, when a signal is present. The CAN high is normally at a lower voltage, minus 0.5 volts shown, and goes high, 0.5 volts, when a signal is present. This is referred to as a balanced line transmission. The signals are inverted and at the start and end of the transmission. This results in good noise rejection. 4 CAN words are shown in the display. This diagram shows a CAN base frame. This shows the typical data present in each CAN word. First is a start frame, then an 11-bit identifier code, next a priority code, which allows important messages to go through first, next the actual message data, a cyclic redundancy check, which is a data integrity check. The message will be rejected if it fails the CRC, and finally an end-of-frame bit.
Welcome to part 3 of our training series, Introduction to OBD2 and Electronic Vehicle Diagnostics. Today we're deep diving into the system that started it all, OBD2. By understanding how OBD2 works, you'll gain a solid foundation in modern diagnostics and unlock the ability to read, interpret, and respond to the messages your vehicle is sending.
This image gives you a clue to the reason for OBD2. In 1988, in order to reduce the air pollution generated by motor vehicles, the state of California in the USA required all vehicle manufacturers to provide an engine control system that could identify faults in a vehicle computer system. This system was called Onboard Diagnostics Generation 1. In 1996, the state of California and the US federal government further required that all onboard engine control module monitors actively perform diagnostic tests on engine emission control systems. This was called Onboard Diagnostics Generation 2, or OBD2. The Federal Test Procedure, FTP, sets maximum allowable emissions levels for OBD2 vehicles. A malfunction indicator lamp, the MIL, must illuminate if a system or component either fails or deteriorates to a point where the vehicle emissions could rise above 1.5 times the FTP standards. Please note that OBD2 is not presently a requirement in South Africa. However, the majority of vehicles in South Africa do comply. OBD2 standards are defined by the Society of Automotive Engineers. They are required by all vehicles after 1996 running on US soil to comply. It's implemented on most but not all vehicles running in South Africa. The standard SAE J1962 16-pin data link connector. There is a generic 16-pin connector that's also used on many other vehicles that are not OBD2 compliant. Standard mandated or generic OBD2 trouble codes are used for identifying vehicle emission-related powertrain problems for the purpose of environmental pollution control. Note the use of the word powertrain, as this means engine only. Manufacturer-specific trouble codes are used for identifying vehicle malfunctions on powertrain, but also include chassis and body electronics. Factory-defined trouble codes include vehicles before 1996. Factory-defined codes may mean different things on different makes and use a non-standard format. The OBD2 diagnostic trouble code consists of 5 elements. The first element is a B, a C, a P, or a U. B for body, C for chassis, P for powertrain, and U for network communication. The second element defines whether it is an SAE-defined or manufacturer-defined trouble code. The third element defines the system in the vehicle, and the fourth and fifth elements are the specific faults. Generic OBD2 powertrain codes are found in the range 0000 to 0999 and 2000 to 2999. These codes will be found on generic code lists and are found within the SAE definitions. Manufacturer-specific codes are in the range 1000 to 1999 and 3000 to 3999. All body and chassis codes are manufacturer-specific. Manufacturer-specific means the same code can have different definitions for different manufacturers. This is why it's always good practice when Googling fault codes to always Google the fault code with the manufacturer name. So you would, for example, Google P1100 VW or P3000 Ford. Factory-defined DTCs can have different formats. Generic OBD2 codes only define emission-related powertrain problems. This basically means engine diagnostics only. Manufacturers allow additional codes to be read and defined under manufacturer codes. But in reality, most manufacturers do not allow other system codes to be read by an OBD2 code reader. The OBD2 system in an ECU can be considered a separate layer. Certain sensor data can only be accessed using the manufacturer protocol. The OBD2 system is not allowed to access this information. Mode 1. Read current diagnostic data. Basically reads what information is available in a controller, usually outputs the number of stored fault codes. Mode 2. Read freeze frame data. The freeze frame is a snapshot of the data available in a control unit when the fault code was stored. This information can give you a clue to what was going on when the fault code was stored. For example, if you read a cam position sensor error and the freeze frame shows that the engine was revving at 10,000 RPM when the fault code was stored, this may give you a clue to the cause of the fault code. Mode 3. Read current diagnostic trouble codes. This lists the confirmed diagnostic trouble code stored in the control unit. It displays the exact numeric 5-digit codes identifying the faults. Note, the definition of the 5-digit code is not part of the OBD2 system. This is part of the OBD2 standard and can be found on the definitions list. Most software, however, has a database containing a list of the definitions. Mode 4. Clear or reset all diagnostic trouble codes. This function is used to clear the emission-related diagnostic information from the engine control unit. This includes clearing the stored, pending or confirmed diagnostic trouble codes and the freeze frame data. This clearing also clears certain learned ECU information, which may result in rough running till the info is relearned, for example fuel trims. Mode 5. Read oxygen sensor test results. This displays the oxygen sensor monitor screen and the test results gathered about the oxygen sensor. The oxygen sensor is a very complex item, and there are 9 numbers available for diagnostics. Mode 6. Read test results for non-continuously monitored systems. In all OBD2 vehicles, the electronic control module actually runs emission tests on each emission system while the vehicle is being driven. These tests are called monitors. These tests are defined and required by OBD2 regulations. In the USA, it is required that all OBD2 vehicles complete a smog exam. One of the criteria is to make sure all the readiness status monitors of systems are complete, or the vehicle will not pass the smog exam. Mode 7. Read pending diagnostic trouble codes. Pending diagnostic trouble codes are set when a malfunction first occurs. If this malfunction repeats, it will become a current diagnostic trouble code or hard code. If the malfunction does not repeat, the code may be stored or deleted, but the warning light will not be triggered. Current diagnostic trouble codes are set when a malfunction occurs during multiple drive cycles, the number of which vary from vehicle to vehicle. This results in the engine malfunction warning light being triggered. Pending diagnostic trouble codes are also called soft codes. Mode 8. Request control of an onboard system. Can be used to enable the offboard test device to control the operation of an onboard system, test, or component. This is similar to the actuation function on professional machines. Mode 9. Read vehicle information. Read vehicle information such as the VIN number, calibration ID, or calibration verification number.
Welcome back to part 4 of our series, Introduction to OBD2 and Electronic Vehicle Diagnostics. So far, we've explored the basics of vehicle diagnostics and the tools we used, and OBD2 system itself. Now it's time to get into the heart of how the vehicle actually knows something's wrong. Modern vehicles are packed with sensors and actuators, constantly measuring and adjusting, and feeding data back to the vehicle's electronic control units. Understanding how faults are detected gives you the insight you need to separate a real issue from a false alarm.
We will generally discuss the basic petrol internal combustion engine. The petrol engine operation is based on the Otto cycle: induction, compression, ignition, exhaust. Induction is dependent on the air-fuel mixture, compression mainly on valve timing, ignition on spark timing, and exhaust once again on valve timing. Compression and exhaust are dependent on valve timing. Valve timing is controlled mostly by mechanical processes. On older vehicles, the air-fuel mixture is controlled by a carburetor. On new vehicles, the air-fuel mixture is controlled by the electronic control unit of the engine. Spark timing on older vehicles was controlled by the mechanical distributor and coil, while on new vehicles, once again, it's controlled by the electronic control unit and coil packs. Older systems use open-loop control. Modern systems make use of closed-loop control. We will now go through the definition of control loops. With a carburetor, the air-fuel ratio is set by the jets. These add a given amount of fuel for a given airflow. This is the same for first-generation fuel injection. This is called open-loop control because the system has no feedback of the actual final air-fuel ratio. Closed-loop control is exercised when an exhaust gas analyzer is used to measure the exhaust output and then adjust the carburetor jettings to perfect the air-fuel ratio. This is the same as with first-generation fuel injection. Closed-loop control in modern engines is achieved by the use of oxygen sensors, which measure exhaust gases and then adjust the fueling in real time. Sensors detect activity, similar to our own sensory organs: sight, hearing, taste, feel, and smell. In vehicles, examples are oxygen. Actuators create motion or activity, like our muscles, or a window actuator or fuel pump in a vehicle. How faults are detected. Faults are detected by the vehicle's electronic control units, which monitor the sensor and actuator signals. These signals should conform to specified values and criteria, for example voltage or frequency. If the signals do not conform to expected values, then the control unit will assume there's a fault. Control units have onboard monitoring and diagnostic processes, which enable the control unit to measure or detect electrical values in the circuits and monitor the responses of actuators when a control signal is changed. In order to detect if the electrical values in circuits are correct or incorrect, the control unit will have the correct values stored in its memory. The same way one would use a multimeter to measure an impedance and compare it with the value in a spec sheet. Electrical circuit check, system performance check, or logic. The monitoring of signals is the root of fault detection. The control unit monitors signals to ensure that they are within a specified range or pattern for each type of signal. If the signal goes outside this range, the control unit will generate a fault code. Probably the simplest signal is a voltage that is either on or off. The signal can be produced by a limit switch, which switches off or on when the device reaches a specific position, like on an electric window, for example. This is an example of a signal where the voltage changes, like a temperature sensor. In this example, the normal operating range for the temperature sensor is between 0.3 and 4.7 volts. If the voltage is outside of this range, above or below the range limits, it will be regarded as a fault. Note that different systems will have different voltage ranges. The signal change can also be a varying frequency signal, digital or analog, like a hot film MAF sensor.
Welcome to part 5 of our series, Introduction to OBD2 and Electronic Vehicle Diagnostics. In this episode, we're tackling a crucial step in the diagnostic process, defining faults. Reading a fault code is easy. Truly understanding what the code means, that's where the real skill begins. Because not all fault codes point directly to a broken part. Sometimes they're just the starting point of a deeper investigation.
Defining circuit faults. Many faults can be defined by simple electrical failures of a sensor, actuator, or wiring. The word circuit in the fault code definition indicates that the fault is likely to be related to a signal problem caused by a fault in the sensor or actuator circuit. This is probably the most useful diagnostic information as it usually indicates positively the cause of the problem. Circuit fault types: circuit or circuit malfunction, circuit open, circuit high, circuit low, circuit range and performance, circuit intermittent. In the following examples, when we speak of the voltage at A, we mean the voltage between A and ground. So in this example, the control unit applies a voltage at A. The voltage at B will depend on the sensor impedance. If there's a break in the circuit, the control unit applies a voltage at A. The voltage at B will be 0. This is the physics definition of an open circuit. The control unit applies a voltage at A, and there is a jumper at C. The voltage at B will be the same as at point A. This is the same as the physics definition of a short circuit. Circuit, circuit high, and circuit low are definitions dependent on the system concerned, and should not be linked to open and short circuit definitions generally, as the actual definition will depend on whether the value is being measured on the supply or the ground side of the circuit. Definition: circuit. The voltage, frequency, or value of the sensor signal is incorrect due to an undefined fault. The sensor voltage could be out of normal range, constant value, or non-existent or corrupt. There's a possible fault with the sensor or wiring, short open circuit, resistance, interference, etc. Definition: circuit low. The voltage, frequency, or value of the sensor signal is either 0, no signal, or the signal is lower than the minimum operating limit. Once again, possible fault with the sensor or the wiring, short or open circuit. Possible fault with the sensor or wiring. It is also possible that multiple sensors are feeding one system and one of the others is faulty. Definition: intermittent. The voltage, frequency, or value of the sensor signal is erratic, irregular, or unpredictable, most likely caused by faulty wiring or connections. It's also possible that internal sensor connections are faulty. Check signal using live data. System performance or circuit range fault. There are many instances where the electrical circuits and the signals are good, where the sensor is reading a value, but the sensor is not performing as expected. For example, the coolant temperature is expected to increase by an expected amount after cold start, but the actual increase is not as expected. Fault detection by logic. In some cases, when a sensor signal does not match an expected value, this can be regarded as implausible. In effect, the signal shouldn't happen under the existing conditions. Sensors may be considered in groups, and their collective output must make sense or be logical. For example, when the throttle is monitored by a throttle position sensor, if the control unit requests that the throttle should be fully open, and the throttle sensor indicates that the throttle has responded correctly, this would indicate correct operation. However, the control unit would then expect an increase in airflow.
Welcome back to part 6 of our training series, Introduction to OBD2 and Electronic Vehicle Diagnostics. In this video, we're going to connect the dots between fault codes and component locations. Because knowing what's wrong is only half the battle. Knowing where it's happening, that's what gets the fix done.
Component locations. In the definition for the fault code P0013B camshaft position actuator circuit open bank 1, B and bank 1 are defined by the ISO standard. The fault code oxygen sensor bank 2 sensor 3. This would refer to the post Cat2 sensor after the second catalytic converter on bank 2, which is the bank of cylinders that does not contain cylinder number 1. Intake, exhaust and fuel sensor locations. Where more than one sensor of the same type is fitted in the system, the ISO standard states that they must be numbered according to their position in the system, starting at the fresh air intake and progressing to the exhaust. Therefore, inlet air temperature sensor 1 will be closest to the fresh air intake. For the fuel system, the numbering starts at the fuel tank and passes through to the engine. Therefore, fuel pressure regulator 1 will be nearest to the fuel tank. Any reference to front, rear, left or right is always taken relative to sitting in the driver's seat looking forward. The letters A, B and C. Where a capital letter is used part of a fault code, for example P242A, exhaust gas temperature sensor, this indicates that the code has been inserted in the fault code numbering sequence as an addition. It enables new fault codes to be inserted in the correct location to keep similar fault codes in the same group. A capital letter as part of the fault description, for example fuel level sensor B, is a manufacturer definition. A or B rocker arm location, for example A rocker arm actuator position circuit high. The letter A refers to the front, the left or the intake rocker arm actuator. The letter B refers to either the right, the rear or the exhaust. The fault codes in this example shows a P0011 A camshaft position. This means that it's the left camshaft. The fault code P0335 crankshaft position sensor A. Position sensor A is a manufacturer definition. The diagram shows the positions of oxygen sensors. The diagram shows the positions of oxygen sensors. This diagram shows engine layout. This diagram shows another engine layout.
Welcome to part 7 of our training series. Modern vehicles are complex machines made up of interconnected systems: engine, transmission, ABS, airbags, HVAC, and more. Each system works with its own set of sensors, actuators, and control modules. When something goes wrong, understanding which system is affected and how it operates is essential to diagnosing the fault correctly. In this video, we'll cover what system diagnostic means and why it's different from just reading fault codes.
Mass airflow sensors convert the amount of air drawn into the engine into a voltage signal. This gives an indication of engine load. This is necessary to determine how much fuel to inject, when to ignite the cylinder, and when to shift the transmission. Diagnosis of the MAF sensor involves visual, circuit, and component checks. This is a list of common MAF sensor fault codes. Most MAF sensors can be checked by supplying power and a ground to the right terminals, and connecting a voltmeter to the signal VG wire, and blowing air through the sensor. It can also be checked using the live data function on most diagnostic computers. For analog systems, most MAF sensors measure from 0.4 to 0.8 volt at idle, up to 4.5 to 5 volts at wide open throttle. Hot film systems measure 30 Hz at idle, up to 150 Hz at wide open throttle. The engine control unit uses the oxygen sensor input to regulate the fuel mixture, which is referred to as the fuel feedback loop. The oxygen sensor. The inside and outside of the bulb is coated with a porous layer of platinum, which serve as electrodes. The interior of the bulb is vented internally through the sensor body to the outside atmosphere. When the outside of the bulb is exposed to the hot gases of the exhaust, the difference in the oxygen levels between the bulb and the outside atmosphere within the sensor causes a voltage to flow within the bulb. If the fuel ratio is lean, not enough fuel in the mixture, the voltage is relatively low, approximately 0.1 volts. If the fuel ratio is rich, too much fuel in the mixture, the voltage is relatively high, approximately 0.9 volts. When the air-fuel mixture is at stoichiometric, the oxygen sensor produces 0.45 volts. This slide explains the functioning of a zirconia-type oxygen sensor with heater. This slide explains the functioning of a broadband-type oxygen sensor with heater. The example shows 2 oscillations or cycles per second, which is the typical frequency for a zirconia sensor under stable operating conditions. Oxygen sensors wear out over time and must be replaced at around 200,000 kilometers. The performance of the sensor also deteriorates over time, so the fuel system performance will also suffer. Symptoms could include poor throttle response, fuel consumption, and surging. These are some typical oxygen sensor fault codes. There are many oxygen sensor fault codes. A marginally sluggish oxygen sensor may not produce a fault code. Waveforms for response times may need to be checked to properly diagnose oxygen sensors. CAN bus fault codes. The fault will be in a specific control unit, for example the engine or transmission, and normally just say CAN bus. CAN bus faults show up in control units due to communication issues on the CAN bus lines. These are some of the other causes of CAN bus faults: resistor failure, failure of the CAN bus cables, failure of control units, failure of voltage or supply, ground to control units, interference in the lines.
Welcome to Part 8, the final part of our training series, Introduction to OBD2 and Electronic Vehicle Diagnostics. In this episode, we're pulling together everything with a general overview of fault codes and the fault-finding techniques.
Fault codes in general. A fault code can indicate the problem area. It doesn't necessarily indicate the fault. Some fault codes can be very specific about the nature and location of a fault. However, many are less specific and can be activated because the signal in the circuit is implausible. The fault could be related to a wiring or connection fault, a sensor or actuator fault, or another type of fault applicable to the system. A fault code may be actuated because the response of a sensor or actuator is not correct due to a fault with another system. The most common one is with oxygen sensors. For example, a small air leak in the exhaust system can cause a significant change to the oxygen sensor signal. Vehicle manufacturers use different terminologies for components, and also different systems may share the same terminologies or names. For example, some fault codes refer to a power steering control circuit, and because they are different types of power steering systems, the fault code could refer to different control systems. For a mechanically driven power steering pump, the code could be due to a pressure control valve. In a system with an electric pump, it could be due to a relay or sensor. So it is necessary to identify the components of a system and the wiring in order to diagnose the fault. In other words, if you're not familiar with the system, you must refer to vehicle-specific information, like workshop manuals. So, you must understand how a specific system works in order to properly diagnose it. This slide shows typical additional information available with a VW fault code. Take note of the additional freeze frame data, fault status, and fault priority. The fault above tells us that the electronic control module has detected the N205 circuit on bank 1 has been or is shorted to ground. Diagnosis will require an understanding of the N205 function and the circuit and the way it's connected to the electronic control module. The diagram shows the schematic location of the N205 sensor. The circuit diagram shows the location of the N205 and its wiring in the circuit. In the wiring diagram, you will see the N205 has battery voltage to it on one side with the key on, and the ECM is the source of the ground when the N205 is activated. The electronic control module is actually monitoring this circuit when the N205 is not active, for the battery voltage that will travel through the N205, and if there's no detective voltage, rather a grounded circuit, this fault code will set. So you'll need to check for the following: the fuse or power, wiring and connections, a failed N205, or a failed electronic control module. In this case study, two faults are present. P3081, note that this fault code does not contain the word circuit. This indicates that it's probably not related to a sensor failure. This is most probably due to a thermostat failure. The next code, P0332, the word circuit indicates a probable sensor failure. The course of action would be to test the sensor. In this specific case, it was found the wire on the NOx sensor on bank 2 was loose. In this case study, both fault codes do not refer directly to a specific sensor. However, if we consider the position of the sensors, we realize that the only sensor ahead of the throttle valve is the MAF sensor. In this case, the faults were caused by a dirty MAF sensor. The following is the generic diagnostic procedure. First, use a suitable machine to read the fault codes. Try to determine which system the fault code lies in. Research the system to understand the way it works, and use this to interpret the fault code. Check the live data for the plausibility of sensor values, Then test the sensor and test the wiring as required. Always check for other fault codes or fault codes in other control units. They may seem unrelated, but it's often the case that one code refers to a symptom, but another code can indicate the cause. Always check whether a signal is part of a CAN bus system, as signals are often shared between control units. For example, the signal from wheel speed sensors can be used by the ABS and traction control systems, but also be used by the transmission and engine control systems. Always check for mechanical faults. A common example is the camshaft-crankshaft position sensor error, which can be caused by a slack timing belt or chain. Try to check sensor values with other tools if possible. Check live data values for plausibility. Do the read values make sense? Don't assume that a code definition is the final answer. Don't assume that all OEMs use the same code in the same way.